Hello and welcome to Friday's edition of Cracking the Cryptic, where I was speaking to Mark yesterday on my return home from travelling, and he suggested it might be worth doing a puzzle that was very hard, as some of our recent videos have been slightly easier Sudokus. So I had just the candidate. I spent a lot of my plane ride home yesterday trying this puzzle by the compiler Shinya, who's been publishing puzzles on Logic Masters Germany. Now, this is a stunning chained killer Sudoku, and some of the logic in here is absolutely beautiful, but it is also savagely difficult. It is so hard. Now, let me show you the Logic Masters Germany site. So here you go. Now the things I wanted to point out to you here, difficulty 5 out of 5. Now not that many puzzles on this site get difficulty 5 out of 5. There are a lot of brilliant solvers who tend to, just churn through puzzles without finding them too hard. Well, this one is hard. Everyone has found it hard. Its rating is 92%, which means it's also very, very good. Now let's work through the rules here. So, normal Sudoku rules. Every dotted cage must contain every number only once. Okay, well that's normal killer Sudoku then. The sums of digits in cages connected by a chain link differ by exactly 1. Okay, so you can see here, for example, this little cage here must be exactly 1 different from this 2-cell cage below it. Neighbouring cages with sums different by 1 may or may not be connected by a chain link. Okay, so it's not necessary for 2 cages that are 1 difference in value to be connected by a chain. There could be a chain, but there needn't be. And you can see there are also these greater than signs in the grid, which are fairly obvious in this version. But if I just show you my version here, I've had to use arrows. So the arrows point at the smaller of the 2 squares. So do bear that in mind. So this square would have to be greater than this square. Now, as I say, I solved this on the plane, so I'm going to take you through the logic of how to solve it. Do have a go at this puzzle first, though. Allow yourself some time. I would say give yourself at least an hour if you want to have a really good crack at it, because it is that difficult to actually make headway. And with that, I'm going to obviously click on the link under the video to find the puzzle, and I will now show you how I solved it. Now the first thing I noticed was that this cell here, a single cell, but it's part of a sort of sequence where, if we imagine this square was an 8 for a moment, the maximum value of these 3 squares would be 9, and the maximum value of these 3 squares would be 10. Well, 8 plus 9 plus 10 is 27. And that would mean that these 2 squares on the edges of row 8 would have had to add up to 18, because we know that the total for any Sudoku, total of any row of a Sudoku will be 45. So we can't have 2 cells in the same row adding to 18. We'd have to repeat the 9. So this can't be 8, this is 9. That's the first thing to note. Now the next thing I'd recommend you do is to try to keep track of forced cages in terms of totals. So if we look at this now, we know this can't go down to 8, because 9 plus 8 plus 9 is too little. It's only 26. These would have to be huge. So we know that this is an incremental cage on this 9. So I'm going to label that blue. So this is 9, 10. Now if we try and come down again, we're going to have a problem, because these 2 squares would have to be 8 and 9. That will repeat the 9. So again, this cage here has to be greater by 1 than this cage. So I'm going to use blue throughout to link cages that have to be greater than the sort of last cage that was determined, and I'm going to use green, I guess, to show cages that must be less than. Now, I think the first significant insight you need to have to solve this puzzle is to notice that the perimeter is entirely connected within cages, within a single, well, there's nothing that sticks out into the middle of the puzzle from these perimeter cages. Now why is that interesting? Well, it turns out to be fascinating, but it requires some thought. So let's ask the simple question: what does the perimeter sum to in a Sudoku? And the answer is not actually that easy to work out, because obviously if I add this row to this row, I can do that very easily. That will be 90, but I'm left with these 7 cells here and these 7 cells here, and I don't really know the value of those. So the thing that you have to appreciate is that these 4 corner squares here get sort of counted twice in the arithmetic. So if I add this row, this column and this column together, I'll get 4 lots of 45, that's 180. But that will be not equal to the perimeter, because in doing that sum I'll have counted these 4 corner squares twice. So the next question is, how does that restrict things? What's the sort of minimum and maximum values I could put in these corner squares? Well, the maximum would be if I tried something like, I could put 9s into 2 of them and 8s into the other 2. That would be the maximum. So that would be 17, 34, 180 minus 34 is 146. So that would be the absolute minimum value for the perimeter. What's the maximum value? Well, same sort of logic. Let's put 1s and 2s into the edge squares. Obviously I can't have 4 1s because these 1s then see each other, they repeat. So if we have 1s and 2s, we'd have to deduct 6 from 180, and that would give us 174. Now, why is this interesting? Well, it's interesting if you happen to spot that this cage here is an 8-cell cage. So its value is quite constrained. The minimum value for this cage is 36. So let's have a think about that in the context of this perimeter. We've got 5 cages going around the perimeter here, and we know they're all connected by chains, and this one is 36. So let's go down: 36, 35, 34, 33, 32. That would be the absolute minimum I could make this perimeter add up to. Now, if we do the arithmetic on that, the average of those cages was 34, and 34 times 5 is 170. So that is very close to our 174 maximum value for the perimeter. So we know already that there's no way there's any big numbers in this perimeter of this puzzle, because it's simply not going to be possible. And in fact, we can go further than that. We can never, if this is 30, we know this is a 36 cage, because if it's any bigger, let's try 37 for example. 37, 36, 35, 34, 33. Well, the average there is 35, and 35 times 5 is 175, and that is bigger than 174, which was our maximum value. So this square, this cage here, is a 36 cage for certain. And we have to be very careful about how this develops. This cage must be exactly 1 less, because if it's 1 more than 36, our average goes too high. 36, 37 for example. Come back to 36 here. This could be 35 and this could be 34, but that average of those cages was greater than 35, and therefore, bang, it's broken. So just remember, 35 times 5 is too big. So 36, this has to be 35. This indeed has to be 34 for the same reason. If I start to go up again and make this 36 and this 35, my average has gone up too high. This cage, on the other hand, could be greater. So 36, 35, 34, if this went up to 35 and this came down to 34 again, we still would just be okay. That would, I think, add to our 174 total. So this one is ambiguous and this one is ambiguous. But this is, I think, the key insight to solve the puzzle. Now, why do I say that? Well, I say it, let's start off by looking at this. We know there's no 9 in this cage because we know it sums to 36 and it's 8 digits in size. So, where does the 9 go in this box? Now, if you look at this carefully, it's quite interesting. We know the 9's in none of those squares, that's obvious. The 9 is not in either of these squares either because of this 9, so the 9 must be in one of those two positions. So, can this be a 9? Now remember, these two cages are connected by a chain. So this can't be a 9 now. The maximum I could make it would be 8. But that would imply these two squares have to sum up to 9 or 7. But they can't because there's already a 9 in the cage. So the 9 cannot go here. It must go there. Now we know there's a 9 over on this side. And we need to think next, I think, about, well, there's a few things we can think about. We know there's no 9 in this cage. So in this box, where does the 9 go? It can't go here, can't go here. It must go in one of those two squares. Remember, it can't go here because this arrow points at the smaller of the two squares. So if I put a 9 here, I have to put a 10 here, or an 11 or something, but any number that's not possible. So there's a 9 down there. We now know there's a 9 in one of these three squares, but remember, we can never put a 9 in the corner because we know that the perimeter total is some number, well, it's either 170, 172 or 174, and therefore the perimeter squares add up to a maximum, corner perimeter squares add up to a maximum of 10 and a minimum of 6. So given that, I can never put even a 7 into a corner square because that would imply the other three squares would have to be 1. Not possible. So the 9 is in one of those squares. So we can see things like there's no 9 in those squares now because they share a cage with this. So there must be a 9 in one of these three squares. Remember, we can't put one in the corner. But that's probably, I don't think we can do much with that yet. Let's have a think about how this develops though, because this cage is 4 cells large. So if this comes down, if we go 9, 8, 9 for example here, then the maximum value for this cage and this cage would be 10. 10 plus 10 plus 9 is 29. These two would have to add up to 16. That would repeat the 9 because we'd have to go 7 and 9 for that. That does not work. So this cage is definitely greater than this cage. Similarly, let's have a think about this cage. If this went 9, 10, back down to 9, we'd have the same problem with 2 10s in this column. So again, this is greater. So we know now that this is a 10 cage, this is an 11 cage. Now, we don't quite know, although this is an 11 cage, it is possible one of these two cages is a 10 cage and the other is a 12 cage. So we can't yet colour in those two cages. But we know this is either a 10 or a 12, therefore it must contain a 1 or a 2. Now, what was the next insight that I had? I think it was thinking about these two columns. Now, the reason I started to think about these two columns was this cage here summing to 11. And you can see there's a chain connecting this cage to this cage, a chain connecting this cage to this cage, and a chain connecting this cage to this cage. Now, that means that these 3 cages here are consuming quite a lot of the sort of surface area of column 7 and column 8, and they're quite limited in value. But given this is an 11 cage, the maximum value I could make these cells would be if I put 12, 13 and 14 into them. Well, 12, 13 and 14 add to 39. Now that is fascinating, because if these squares take their maximum value and are 39, what's the value of these squares here? Well, the answer is 90 minus 39 is 51. So I've got to make these squares equal 51. But let's think about how we're actually going to be able to do that. So first things first, 9, 10, 11, these add up to 30, therefore these two add up to 15. Therefore, without using a 9, these two squares are 7 and 8. So the maximum value for these two squares now is if I make them equal 10, because this is an 11 cage. So the maximum I can make those two squares would be 10. And you can see to do that, I would have to use 4 and 6. So let's just imagine that's what we did. So we've now got 39 plus 10, that's 49. So I need these squares here to add up to 41. Well, the maximum I could make these 3 squares would be 24 if I made them 7, 8 and 9. And that would mean these 2 squares had to be 17. Well, there's only one way of getting to 17 in 2 digits, and that's with 8 and 9. So this is such, I think, a really important part of the puzzle, is to notice that this column is really constrained. These 2 squares have to be 8 and 9. These squares have to be 7, 8 and 9. And we can go further than this because of the beautiful geometry that Shinya's used on the puzzle. So we knew that there had to be a 9 in column 9, and we know it's in none of those squares because of the 9 in one of these 2 positions. So we know there is a 9 in one of these 3 squares. Therefore, this square here can't be a 9. That's got to be the 8. That allows us to do a bit more logic like this. And now we can tidy up the 8 and the 7 there, look. And we can ask where an 8 goes in column 9. It can't go in any of those squares because there's already an 8 in the cage, so it must be in one of those 4 squares. Now that means this square has to be a 7. And that gives us an 8 there. Very, very nice logic. We know these are all maximal, so we can colour them all in blue. Where can an 8 go now? In column 9 again, given these 8s. You can see, because these 2 squares can't be an 8 because they're part of this cage, this is the only valid position. Must be a 7 in one of those 2 squares because of this 7 here. And as these 2 squares do have to add up to 10, this has to be a 1. These 3 squares are 2, 3 and 5. And the next thing I think I noticed was we can now think again about the total for row 9 of the grid. And why do I think that? Well, we know this is 36, this is 35, this is 34. So the possible values for this cage here are 35 and 33. Now if this was 35, 35 plus 8 is 43. So these 2 squares would have to add up to 2. So they both have to equal 1, which is obviously invalid. So in fact, this cage here must add up to 33, and therefore it continues to progress downwards. 33 plus 8 is 41. So these 2 squares become 1 and 3. And okay, so what should we do next? One thing we could do is to think about this column. because we know that either both of these cages equal 12, or one of them is 10 and one of them is 12, so that the value for these 7 cells is restricted. It's either going to be 12 plus 12 plus 9 equals 33, or it's going to be 10 plus 12 plus 9 equals 31. So what are the values for this square? Well, if these add to 33, these two have to add up to 12. So you can see this can't be 1 or 3 anymore. It can't be 2 in that instance. It could be 4. It could be 5. It can't be 6 because 6 would be repeated. And it could be 7. It can't be 8 or 9. So up here, this would have to be 5, 7 or 8. In fact, the 7 here rules out the 7 there, and that rules out the 5 there. Now the other possibility would be that these add up to 31, in which case these two have to add up to 14 without using 9. So they have to be 6 and 8. So that could be a 6 and that could be an 8, which is already catered for. Now this is interesting though. So if we come back to this box, we've got these numbers placed. So we know that the choices for these 3 squares here are 1, 2, 3 and 5. Now, as this is a 1 or a 3, we know that there's a 2 and a 5 in these 3 squares. So ask the question, can these 2 squares be 2 and 5? And the answer is clearly no, because if this was a 2-5 pair, we'd have to put a 2 and a 5 in these 3 squares. But neither of these 2 squares can be a 2 or a 5. So this is not a 2-5 pair, therefore this does include a 3. Therefore, this doesn't include a 3. And just as importantly, if we know there's a 2, 5 in one of these 3, and we know that one of these squares is a 2 or a 5, this square must be a 2 or a 5. We must have a 2 or a 5 in one of these 3 positions, and this is the only position that's valid. And look at that. That creates a 2-5 pair in column 3, which is really, really cool. Now it's cool for a few reasons, but the first thing I noticed is where can we now place an 8 in this box? Now we have a couple of 8s in the grid. We can never put an 8 in this box because we know that the maximum value of this is 12. So if I try and put an 8 in there, I'd have to have the other 3 squares adding up to 4, which is impossible. So there's no 8 in any of those squares. Now, if I put an 8 in this cage, in one of these 2 positions, this is an 11 cage, so it would have to be 1, 2 and 8. But I've already got a 2 in the column, so there's no way the 8 goes there either. So the 8 is forced into this square. And now we know that this must be a 12 cage because it can't be a 10 cage because there would have to be a 2 here. There's already a 2 in this box. So that becomes a 4. That removes, well, this now has to be a 5 up here because of the 8. This has to be a 7. This cage here is 1, 2, 3 and 6. To complete the column, these 2 squares are 1, 3 and 6. And what could we do next? Just trying to remember what I did now. Ah, yes, 8s. Where can 8 go up here? Well, if we put an 8 into this cage, we know this cage equals 10, so that would be an 8 and a 2. That would repeat the 2. So this is not 8. The 8 is up here. So now you can see there's an 8 in one of those 3 squares, but again we can do better than that. If I put an 8 here, because of the arrow, the 8 is being pointed to, it's the smaller number, I'd have to put a 9 here. So we'd have 9 plus 8 is a 17 cage. But this cage is a 14 cage and it's connected by a chain. So the 8 is not there, and that gives us an 8-9 pair in this box. You can also see these 3 digits have to be 7, 8 and 9 because of the 7, 8 and 9s here and here and here. Now, what next? yes, we can think about this cage now. I mean, this is such clever puzzle design. It really is, because now we've got a handle on the value of this cage. And if you remember, 36, 35, 34, we know this cage is 33. So we know that this cage is either 34 or 32. But if it's 34, these three cells would have to sum up to 11, and one of them is a 7. So these three squares would have to be 1, 3, and 7. Well, that gives no possible value for this square here. This needs to be a 1 or a 3, so we can't have 1, 3, and 7 into those three squares as well. Ergo, this is not 34, it's 32. So it continues its descent. Now this is so important now because, well, firstly, we know these three squares add up to 13. One of them is a 7, so the other two must add up to 6 without using a 5. So this becomes 2, 4, and 7. One can't be 7, look, because of the 7 over here. And now we know the value of the perimeter, because we know that actually it continues to descend downwards the whole way. Therefore, it averages 34, which means the perimeter adds up to 170, which means these corner squares must add up to 10. Now, if these two add up to 4 at the bottom, these two have got to add up to 6. If this is a 2 or a 4, therefore, that one is also a 2 or a 4. So finally, we get these corner squares locked down. Now, let's have a think about this. We can't, there's a 2 in one of those, so there's no 2 there. There must be a 2 in one of these two positions. This square is part of a 10 cage. So you can see the options for this square in theory are 1, 3, and 6, but it can't be a 1 because that would repeat the 9. So this is a 3 or a 6. This is a 7 or a 4. There's a 1 in one of those two squares, and therefore there's no 1 in one of these two squares. And now we can do a little bit of logic with the arrows. So this arrow is interesting. So if we try and put a 1 in here, we'd have to put a 0 below it, so that, or above it. That's not allowed. If I put a 3 here, as there's a 2 already in this box, this would have to be a 1. So we'd have a 3 here and a 1 here. And that would break that square, look. So, in fact, that can't be a 9 either. So this can't be a 3. This needs to be a 6. And similarly for this square, look, this square needs to be greater than this square. So this can't be a 2. And if this can't be a 2, this must be a 2, because we know that there's a 2 in one of these two positions. Okay, so I think let's have a quick look at the central 3x3. You can see it's completely contained by 3 cages which are connected by chains. So 45 divided by 3 is 15. We know the average of these cages must be 15. It must be a 14, a 15, and a 16 cage. And the 15 cage has to be the central cage, so it has to be the middle cage, the cage that connects to both other cages. So this is a 15 cage, which means that it's either 6 and 9 or it's 7 and 8, and we don't yet know which of those is going to be correct. Now, if we have a look across row 1 of the grid, we've got a 2, 4 pair there, look, so these 3 squares have got to be 1, 3, these 3 squares have got to be 1, 3, and 6. And that allows us to disambiguate the value of this cage. We know it's connected to a 13 cage, so it's either 12 or 14. If it's 12, it would have to be 8, 1, 3, and that would repeat and break the top row of the grid. So it's not 12, it must be 14, which means these two squares add up to 6 without using a 1. So these two squares are 2 and 4, which means this must be a 7. These two squares now have got to be 5 and 7 to complete the box. And there's a 7 there, look. So That's a 7. That's a 5. We know this is a 14 cage, so these have to either add up to 13 or 15, therefore that's got to be an 8, and this is the 9. You can see there's a chain link here, 14 and 15, so that's working nicely. Okay, so we can do a bit of tidying up. Look, we can delete 9 from both of those options. If this isn't 9, this can't be 6. We can delete 8 from this option, therefore this can't be 7. That can't be 8. That can't be 7. Now, what next, you may well ask? Well, I don't think this was necessarily important to solve it, but one thing I did notice is if we have a look at row 4 of the grid and ask where a 9 can go now, because of this arrow, because we know that this square must be lower than a 7, there aren't many places a 9 can go. A 9 can't go here because there's already a 7-9 pair in the column. So these two can't be 9, these two can't be 9, that can't be a 9, that can't be a 9, so 9 can only go in that square. Oh, I'm about to sneeze. Okay, so now let's look at this. We've got 9s into those squares. There must be a 9 in one of these two positions. And tidy up that. That can't be a 6. And I think the next thing I looked at was this cage here. Now, we know this cage sums to 35, so if I remove an 8 from it and add this 8 in, these squares must sum to 35. Therefore, these 3 squares must sum up to 10. But these squares here, look, are part of these two cages. And we know this is a 13 cage and this is a 14 cage. So these cages together sum to 27. Minus 10 means these 5 cells must equal 17. 17 plus 8 is 25, so these 3 squares have got to sum up to 20. Now that is quite cool because all of a sudden this square becomes very restricted. You can see immediately if I try and put something as low as a 4 into this square, for example, because I know there's a 9 in one of these two positions, 4, 9, I'd have to put a 7 in the column. That's going to break. Same thing is true of 3. If I try 5 in this square, that's not possible for a different reason. This is obviously a 12 cage. So if I remove a 5 from the options down here, I can never get as high as 12. So that can't be 5. How about 6? 6 is possible. I'd have to make these two squares 5 and 9. What about 7? 7 is also possible. These two squares could be 4 and 9. Can't have an 8 because there's already an 8 here. Can't have a 9. So the actual options for this square come down to 6 or 7. Now let's have a think about whether that influences either of these two squares. Well, we know this is a 13 cage, so it must include a 1. Therefore that can't be a 1. So this can't be a 5. And what did I do next? I think, oh yes. Yes, I think what I did was I looked at these 8s and I noticed that that meant that there were 8s in one of those two squares in the centre. Now, if you have a look at this square here and consider whether it could be an 8, it gets very interesting. Now, why do I say that? Because, well, the first thing to note is that we don't yet know if this is a, or we didn't know whether this is a 14 cage or a 16 cage. But all of a sudden, if we try an 8 here, it has to be a 16 cage because of this 2. because if it's not, these would have to be 1, 2 and 3, and that breaks. So all of a sudden these 3 squares have to add up to 8 without using a 2, so they'd have to be 1, 3 and 4. Which means these squares down here, because obviously this is a 6 and this is a 9, these squares down here become 2, 5 and 7. Oops. But this is a problem. Now why is it a problem? It's a problem because where do we put a 6 in this block? This 6 and this 6 interact very nicely to force the 6 into this square. And now we have a 6 and a 7 in those squares, and this square is broken. So we know, in fact, with a little bit of thought there, that the 8 is not in this square. It must be here. Which gives us an 8 and a 7. Removes the 7 from this square. Locks the 7 into one of those 2 squares over on this side. Now the next thing I noticed, which is a difficult one, is we know that this is a 14 cage. So let's have a think about how we can make 14 in 4 cells. Well, one way would be 1, 2, 3 and 8. Well, that's ruled out. The next way would be 1, 2, 4 and 7. Well, that's ruled out. Now once we start to get into combinations using 6, it's interesting, because if we had 1, 3, 4 and 6, that breaks this square. So the only option that's valid with a 6 would be 1, 2, 5 and 6. Let's put that in just to show you. That's valid. I can't see a reason that doesn't work. Now the only other possibility would be we don't use a 6 and we go down to 5, in which case 2, 3, 4, 5 would be the valid combination. So we now know for sure that this 14 cage is either 2, 3, 4, 5 or 1, 2, 5, 6. Now the thing you've got to appreciate there is that either of those definitely contained a 2 and definitely contained a 5. Now why does that matter? It matters because it limits this square very slightly, but just enough. Once this square can only be a 1 or a 3, we can obviously eliminate the 1 and the 3 from these 2 squares. This becomes a 2, 5 combination. But the critical thing now to realise is that there is a big problem with this square being a 1. Now if you can't see that, do pause the video, because it's not easy to see. But let's have a look at it and let me show you why. If this is a 1, this square suddenly becomes a 3. And you may say, well, why does that matter? Well, it matters because now these 2 squares have got to be 1 and 7. We know this is an 11 cage. We know that this is now 6, 4. So this has to be 1 and 7, which would have to look like this. That looks the 7 there, obviously. And I'm sure you've all spotted the problem, but the juxtaposition of these 1s here is terminal for this box, because there's nowhere you can put a 1 in the box anymore. It completely breaks it. So this square cannot be a 1, and that was the critical final step in the logic which allowed me to crack the puzzle, because once this is a 3, suddenly things start to get a little bit easier. We start to go round like this. These 2 squares now have got to be 1 and 5 in some order. What did I notice next? Now once this is a 3, this has to be a 2 and this has to be a 7, which gives us a 7 up here and locks this to be a 3. That gives us a 1, 6 pair here, means that's got to be a 3. The 2 here means this is a 5. The 4's in one of those means that that square up there is a 2. That gives us the 4 and the 2 over on the left hand side of the grid. These two squares you can see have to be 3 and 6 to complete the column. That's now achievable. This isn't 2. These two squares have got to be 4 and 5 in some order. We don't yet know what that order is, except that we do know the correct combination for this 14 cage now. It can't contain a 3, so it's not 2, 3, 4, 5. It must be a combination involving a 6, and therefore it must look like that, because we know it doesn't contain a 3. Now that resolves the 4, 6 at the bottom. These can't be 1 anymore, so we need 3, 4 and 5 into these squares. That one can't be a 3. These two squares have got to be 4 and 6. Let's just tidy that up as well. This can't be 5. Okay, that can't be a 1 or a 2 or a 6. 3 like that. None of those can be a 5. That one can't be a 2. And these 3 squares here need to be 1, 4, 5 and 6 in some order. And that is quite interesting, because if we think about now where the 9 can go in this box, if we try and put the 9 into this cage, what happens? We could pair it with a 1, but the minimum value I could make these 3 squares would be 1, 4 and 5, i.e. 10. 10 plus 9 is 19. Now I know that this cage either equals 14 or 16, therefore I cannot put the 9 here. So the 9 has to be down in one of these 2 squares. Therefore this must be a 9, and this must be a 4, which resolves the 4 and the 6 over on this side, look. Removes the 6 as an option here. The 5 resolves the 5 and the 1 over on the left hand side. This has to be a 2 or a 6 all of a sudden. 7 here means this is a 9. I could have got that before. But in fact, the irony of these 3 digits is that they really don't help very much with much in these columns. I mean, the 9 fixes that that's a 9, but that's, I think, the only progression we're able to make as a result of disambiguating these 3 squares. Okay, so now if we have a look at these 2 squares, you can see the options are 1, 2 and 3. We know this cage either equals 14 or 16. It's now no longer possible to get as high as 16, so we have to somehow get to 14. Therefore these have to be 2 and 3. That gives us a 1 here, 6 here, 2 here, 6 here. 1, 4, 5 here all of a sudden. Now the final point is to notice something quite interesting about these 3 squares and these 2 arrows. So this square is always got to be the lowest it can be. Now given that we know there's a 4 among these squares and we know there's a 6 amongst these squares, the other digit that could be in here is a 2 or a 5. Now as this is always going to be the lowest number it can possibly be, it's either going to have to be a 4 or a 2. So if the 2 is in here, the 2 will be the middle digit. If the 2 is not in here, the 4 will be the middle digit. Now why does that matter? Because look, 2, 4 here, 2, 4 here. There is now a 2, 4 pair in column 5, which allows us to disambiguate this 3, look. mean, it's so clever, this. It really is. I mean, it's... Now that must be a 5 as well by exactly the same logic. 5 here means the 2 is in there, which allows us to disambiguate everything. I mean, it's a stunning, stunning execution. But, as I said before, or I said at the start, or I certainly intended to say at the start, it is savagely hard. It really is. 1, 4, 5, 4, 6, 6, and 1. And that is how to solve this absolutely beautiful puzzle. So Shinya really struts his stuff with this Chained Killer Sudoku. I hope you had a go. I hope you enjoyed it. Do let me know if you found some better logic than I did. And we'll see you again soon on Cracking the Cryptic.